Okay, now we're going to move on to looking at beams that are fixed ends. Now, my picture for fixed ends looks something like this. The way I think of it, actually, usually in the classroom, I kind of talk about this with the blocks on the wall, do you know what I mean? So, here's rows of blocks. Something like this. There's 3 rows of blocks. And you've like there, something like this anyway. So these are blocks on the wall. So if you imagine taking this off, this off, this off, this off, and this is looking sideways, but putting a beam into the wall there. Now, obviously, the dimensions of the beam have to be such that it fits in this gap here. You can even take this block away and this block away, and it's just sitting there like that. There's nothing causing the beam to come out of the wall straight, so it's simply supported. But if you have the beam sitting there on the wall and you put the blocks around it, and particularly the blocks on top and more blocks. Now this mightn't actually how fixed end beams live in the wild, but it's a good explainer. So the beam is in here. This is so the beam is coming out of the wall like this. Then what these blocks on top are doing is they're, look, we have it here, they're enacting a moment and causing the beam to come out of the wall straight. So this is what a fixed end beam kind of does. So that's how I explain in the classroom. If I was to draw it, the picture of a wall, and then the important thing is that it comes out of the wall straight. Now it can almost certainly, almost immediately start deflecting, and there's something going on called hogging, but the important thing, it comes out straight. Of course, it's the loads that cause it to deflect. Something like this. That's obviously not a good picture, because in particular I want this to be the neutral. That didn't come out too bad. So this would be the x-axis here. This is x equal to 0. This is x equal to the span of the beam. And in terms of the differential equation, you've got 4 anti-differentiations, and that means you've got 4 constants. You've got RA, MA, C1, C2. So you need 4 initial conditions. And these are the conditions. So as you can see, like, you've got a deflection here. A deflection is this distance here, which is not the same as a slope, not the same as bending moment. But here you can see there's no deflection, there's no distance between the neutral and the position of the beam. So the deflection here is 0, and what that does is that gives you C2 is equal to 0. Okay, and over here you have the deflection. So this is the deflection at the end at L, which is the span of the beam, is 0. Now what else? The beam comes out straight. So what that means is, if you look at the slope at these points, it's 0. So that's in contrast to simply supported. So before this blocks are put on, this is like a simply supported beam, and you see the slope is negative. But once that force is applied, the beam is going to come out, start straight. So the slope here, so that's y dash, the slope at 0 is 0. And we've said once or twice before, and we'll write it down below as well, is that the C1 is proportional, so it's a constant times the slope at 0, and the slope at 0 for fixed ends is 0. So this means that for fixed ends, C1 is equal to 0. So both C1 and C2 are 0 for fixed ends. Now, C2 is always 0, so that's in Math 7019. And C1 is 0 for fixed ends, and it's also going to be cantilevers, we see a little bit later, but C1 is not 0 for simply supported, it's merely negative. So that's C1 and C2 sorted, they're both 0, but what about MA and RA? Well, what you have to do is you have to apply two boundary conditions, that the deflection at the span is 0 and the slope at the span is 0. And what you get is simultaneous equations, two of them, in RA and MA that you have to solve. MA is not 0, as explained here. For fixed ends beams, there is a non-zero moment keeping the beam straight. So this is simply supported, but the blocks or whatever, that causes a moment, so MA is not 0. This is absolutely vital. Because of that, MA is not 0. In general, if we think about it, the bending moments we talk about are positive. So if you calculated bending moments in the previous section, they were all coming out positive. And positive means that it's making the beam go in this direction. That's a positive bending moment. Now so that's causing it to go clockwise, is positive. Now look at this force, it's forcing the beam to go the other way, which is anti-clockwise. And so for fixed ends, not only is MA non-zero, we can actually say that MA is negative. So if you get a positive bending moment for fixed ends, you know you've made a mistake. Okay. What do we got? However, this moment causes the slope to be 0 both ends and deflection is 0 both ends. Okay, so if the following four boundary conditions, y of 0 is 0, y of L is 0, y dash of 0 is 0, y dash of L is 0. MA is non-zero. We will have that C2 is 0, we'll have the C1 is 0. And this is, and now I've written for Math 7019, and these are for fixed ends and cantilever in Math 7019. Well, I think they're always actually. Well, no, it's possible in weird scenarios, but for Math, this is just for Math 70019. What we have is, this is just showing stuff we said before, but didn't write. So in Math 7019, the deflection will be 1 over EI times stuff that equals 0 at 0 plus C2. So if you substitute in x equals 0 into this bit is 0, and this is y of 0, and the deflection 0 is 0. So y of 0 is C2 over EI, and it follows that C2 is EI times the deflection 0, EI times 0 is 0. So C2 is 0, and that's always. Okay. And then you're always going to have that the slope is 1 over EI times stuff that equals 0 at 0 plus C1, which implies that the slope at 0 is 0, and it's all this will be 0, this bit. So you'll just have 1 over EI times C1, C1 over EI. So C1, if you multiply out, is EI times the slope at 0, and the slope at 0 for fixed ends and cantilevers is equal to 0. So you have EI times 0 is 0. So C1 is 0 for fixed ends and cantilevers, but C1 is negative for simply supported. And if you mess these up, just the way the marking scheme goes, you're not going to go well. Okay. Right, let's go. So this is a kind of straightforward question. A light beam of 6 meters has both ends embedded in walls. Draw a picture of an unloaded beam with fixed ends, which explains why the boundary conditions are given like this. So here it is. So we see that the deflection is 0 at both ends, and you can clearly see from the picture that the beam, even if it's loaded, is going to have a 0 slope. That's all that's looking for. Okay, now let's do a proper example. Look at here. A light beam of span 6 meters is fixed, so you'll have to hone in on this, at its endpoints. At points 1 and 5, there are point loads of 36 and 36. So they're both 36. And you might notice here there's a symmetry here. By solving this differential equation, m double dash of x equal to minus w of x, the otherwise we're not going to worry about. Express the bending moment in terms of step functions, RA and MA. Okay. So little picture. So for fixed ends, we'll draw something like this. And the reason what's very important about drawing is it reminds you about the boundary conditions. So it reminds you that the deflection being 0 is easy, but it reminds you that the slope at both the endpoints is 0. And see, it's more engineering that tells you that rather than maths, as it were. And what have we got? Point loads at 1, 5. Now this is a particularly easy question. Well, not particularly easy, but this is a bit easier because the total load is 72, and it must be shared between RA and RB. But because it's so symmetric, if they add up to 72, and because it's symmetric they're equal, they must be 36. So RA is equal to 36, and that makes things easier. But just to show the method for if it's not symmetric, I'm going to do it the long way, basically, not pretending that. Okay, so the loading is 2 delta functions, 36 delta x minus 1 plus 36 delta x minus 5. Right. So now we solve the differential equation. The differential equation is m double dash of x is equal to minus this. Now minus this, if you like minus 1 times this, minus 1 times this will be minus, and minus 1 times this will be minus. So where are we at? M double dash of x is equal to minus 36 delta x minus 1 minus 36 delta x minus 5. So there's an or otherwise written in these, and that's how you'll be doing it next semester, where you just go, oh, delta goes to u, goes to square bracket, 2 anti-differentiations, delta goes to u, goes to square bracket, and I have RAX plus MA. I don't recommend doing that at this point. So anti-differentiate both sides twice. Fix the constant minus 36, antiderivative delta is u. Fix the minus 36, antiderivative delta is u. And you pick up a constant at this point, RA, which we know to be 36, but we'll pretend that we don't know. And we go at it again, m of x. Fix the minus 36, antiderivative of u is square bracket. Fix the minus 36, antiderivative of u is square bracket. Antiderivative constant RA is RAX, and pick up another constant at this point, plus MA. Now, in contrast to simply supported, you can't actually find RA and MA at this point, because I'm not exactly sure how it works, but it's like you don't know what the actual, you don't know what this, well, there's no way to really find this out. How you find it out is, you know, it is the force, it's whatever the force is needed to make it come out straight, but you don't have slope here. Like, this isn't slope, m dash of x, that's actually shear force. It's the slope of the bending moment, but it's not the slope. So you can't find RA and MA at this point. Okay, that's the first part. Second part of the question, the deflection y of x at any point on the beam, and actually just before I go on, it said give me the answer in terms of RA and MA, which I did. And I can't say MA is 0 for a fixed length. Deflection y of x at any point in the beam is found by solving this, solve this. We anti-differentiate, blah, blah, blah. Okay, so we're going to have 2 more. Right, so EI times second derivative y double dashed of x is equal to bending moment, which is this. And this again we see with the notation, you want to be careful. Like, it's very easy to anti-differentiate this again if you're not quite clear what you're doing, and and you'll end up anti-differentiating 5 times, which is wrong. So I write this down carefully. EI times second derivative equals m of x. M of x equals to this. Like, if you leave out the m of x, you're just in trouble, I think. What have we got? Minus 36 square bracket x minus 1 minus 36 square bracket x minus 5 plus RAX plus MA. And we're going to end up, as it says there, with 2 more constants. So anti-differentiating the left-hand side, fix the constant EI. Now, they look like variables, but for a single beam, E and I are constant. Antiderivative, second derivative is first derivative. Fix the minus 36. We know at this stage antiderivative square bracket is square bracket squared over 2. We can go a bit faster at this stage. Square bracket squared over 2. Plus, now fix the RA, it's constant, and the antiderivative of x is x squared over 2. And the antiderivative of MA is MAX, and we pick up a constant C1. You could get rid of that at this point because you know that's proportional to the slope at 0, and for fixed ends and indeed cantilever, slope at 0 is 0, but we'll just keep it just for the time being. We'll anti-differentiate a second time. Fix the constant EI. Antiderivative of first derivative is the original function y of x, which is what we're looking for at this point. Minus 36 divided by 2 is minus 18. Antiderivative of square brackets. I might have time to fix this. Oh no, it's going to be down here. Well, yeah. So square bracket cubed over 3. Minus 36 over 2 is minus 18. Square bracket cubed over 3. Now here it gets a little trickier. So you've got RA divided by 2 by x squared. So there's different ways of explaining this, but say, where will I write it? I'm going to go up the top of the page. So RA x squared over 2. RA x squared over 2 is the same as RA times x squared. Now what's divided by 2? It's the same as a half. And then order of multiplication doesn't matter, so this is the same as RA by a half, which is RA divided by 2 times x squared. So I can see RA x squared over 2 as RA over 2 times x squared. And if I want to anti-differentiate that, fix the constant RA over 2 and then anti-differentiate x squared. So fix the constant RA over 2 and the antiderivative x squared is x cubed over 3. What I tend to see as a mistake is people will do x cubed over 3, and that's not correct. Because, well, it's kind of shown up there. Actually, it should be RA x cubed over 6. Fix the constant MA. Antiderivative of x is x squared over 2. Antiderivative of C1 is C1x. And the final constant C2. Now, use the boundary conditions. C2, any beam whatsoever in Math 7019 is 0. And for fixed ends, because the slope at 0 is 0, you find that C1 is also equal to 0. So that's not, if you do that for simply supported, you're just going badly wrong. But for fixed ends, yes. Right. So what we end up with is EI times y of x. 18 over 3 is 6. 18 over 3 is 6. So this is half by a third, which is a sixth. So you got RA by 6, which is RA divided by 6, x cubed, plus MA over 2, MA over 2, x squared. And what we want to do now is find RA and MA. So what we're going to do is we're going to write down two equations to generate, well, we're going to write two boundary conditions that gives us two equations in RA and MA. And the two equations are, the first one is that the deflection at 6 is equal to 0. So we're going to go into this and put x equal to 6 and get out 0. That will be an equation in RA and MA. And we're also going to say that the slope at the end of the beam is equal to 0. So the slope, we do have it. It is just back here. So I know if we sub in x equal to 0 into this, we get out 0. And that will give us a second equation in RA and MA. And if we have two equations and two unknowns, we'll be able to find it. Right. So y of 6. So I'm looking at this yoke. So I think what I'm going to do is probably just write on the left here. We'll see what happens. Okay. So EI times the deflection at the end of the beam at x equal to 6. So we've argued that must be Ci times 0. So EI times 0 is equal to 0. So EI times y of x. So if we put x equal to 6 into this, we get out 0. So we get minus 6 square bracket 6 minus 1 cubed minus 6 times 6 minus 5 cubed plus RA over 6 times x cubed, 6 cubed, plus MA over 2 times 6 squared. And we know that this must equal 0, so we'll do that over here. So what I'm going to do is I'm going to bang all this into the calculator, and it's going to be a negative number. I'm going to add it to both sides, get a nice little equation in RA and MA. So the things in the square brackets are positive, so square bracket of a positive thing is just itself, so no issue there whatsoever. Okay, so I get minus 6 times 6 minus 1, don't put that into the calculator, it's 5 cubed. Minus 6 by, now that's 1 cubed, that's just 1, so minus 6 by 1 is just that. Now here, yeah, well that's all I need for here. So that's minus 756, so add that to both sides. And then be a bit clever here, 6 cubed divided by 6 is going to be 6 squared, that's 36, or A. 6 squared is 36, divided by 2 is 18, MA. And then adding the 756 to this gives you 0, and 0 plus that is the same thing, and then 0 plus 756 here. So that's your first equation. Now, of course, if you exploited the symmetry that said RA was equal to 36, you wouldn't be long finishing this question off, but we're just show you how it works. I'm going to pretend you didn't see that. So that's the first initial condition. The other one is that the slope at 6 is equal to 0. So similar story, EI times the slope at 6. Now, slope at 6 is the slope here. It's not like positive, like simply spotted, it's 0. EI times 0 is 0. So if I get this is equal to something, I know this something must be equal to 0. Again, I recommend a lot of notation here. Very easy to just write down something is equal to 0, or yeah, you'll see it in the feedback I give to your work. Okay, now about 6 minutes left in this video, so gotta move. Now I'm going into y dashed of x, which I have from back here. So minus 36 over 2 is minus 18. Square bracket, 6 minus 1 to be squared. Minus 36 over 2 is minus 18. Square bracket, 6 minus 5 to be squared. Or over 2 times x squared, 6 squared. Plus ma times 6. And of course, C1, as we said, which is proportional to the slope of 0, is 0 for simply supported. Sorry, so the C1 is 0, so I don't include that. But we know that this whole thing must equal 0. So that's a second equation, or in MA. So I'm going to bang this into the calculator. Minus 18 by 6 minus 1 is 5, squared is 25. Minus 18 by 1 squared, which is minus 18 by 1, which is minus 18. Minus 468. So this bit is minus 468. So I'm going to get rid of that by... See, yeah, so the other thing I don't like to see is, see this? I'll see students, that's the EI times the deflection at 6. They find that and they suddenly end up with an equation. That's not great maths. So I'm saying they write this and then this. How do you get from there to there? It doesn't quite make sense. You can get from here to there though. So that's what I mean about being careful. So anyway, we're going to add the 468 to both sides. And we're left with 6 squared is 36, divided by 2 is 18. 6 by MA is 6MA, equal to 468. And we have two equations and two unknowns. We should be able to solve this handy enough. We probably don't need no Kramer's rule or anything here. I would prefer the answer in terms of fractions, but it's not completely necessary if you want to do 4 significant figure rounding. That's not the end of the world. For me, I don't know. It doesn't really matter, does it? Sure, I could multiply this one by minus a half, couldn't I? It doesn't really matter. You should have good practice from simultaneous equations from chapter 1 anyway. So minus a half by minus 36 is minus 18 RA. Minus a half by 18 is minus 9 MA. Now we'll be looking to get a negative MA, that is important. And 756 divided by 2 and I get minus 378. Add these two yolks together, and I get minus 3ma equal to, looks like minus 90 to me. A bit tired, so I'll just make sure, yeah. No, plus 90, because I want ma to be negative. Although if it comes out positive, I can't just make it negative. I just have to say I've made a mistake and hopefully go and find that. I want to get rid of that minus 3. I can do so by dividing by minus 3. Because that will get rid of multiplied by minus 3. So ma is equal to minus 30. And it is good that that's negative. And then I want to throw that into one of the equations to go and find Ra. So I'm going to go from here. I'm going to take a shortcut because I want to write my answer. I'm going to take away 6ma from both sides. Do you understand? Because I want to get Ra in its own. So take away 6ma. That'll get rid of that, and I have 18 Ra is equal to. If you're a bit stuck, you can just kind of just do it your own way. Like there's a million ways to do these simultaneous equations. 468 take away 6 times ma, which is minus 30. And so I get 18 Ra is equal to, what have I got? 468 minus 6 by minus 30 is plus 180. Is equal to 648. And then I want to get rid of that 18. And we're expecting to see 36. Let's get rid of multiply by 18, divide by 18. Yeah, thank God. Now the last thing, remember, we were asked to solve, I have to go fast now because I'm running out of time in the video. We're asked to solve for y of x. So divide both sides by ei. It's written on the next page now. Y of x, divide both sides by ei, or multiply both sides by 1 over ei. We have minus 6, this is taken from the previous page, x minus 1 cubed, minus 6 square bracket x minus 5 cubed. Now Ra is 36, and it's 36 divided by 6, which is 6. And then the ma is minus 30, good that it's negative, divided by 2 is minus 15. Minus 15x squared. C1 and C2. So this is what we end up with. Here's a graph of this. Now it's very hard to see what this thing does. It doesn't look like it's flattened, but just at the very last minute it flattens. But remember, it's kind of, well, I don't know what the units of this yoke are. So this goes flat at the very last minute. Here we can see the symmetry and the deflection. So it's because they're at 1 and 5, it's a symmetric story. So there's a symmetry there. And the fact both the deflection and slope is 0 at the end of the beam. The larger the value ei, the less the deflection. So if this is a big number, you divide by a big number, it's very, very small. And note also by symmetry that the slope here is equal to 0. I'm just going to call this x max. I'm going to go fast. I think I've got about 5 seconds left. There's one more question to draw a picture, and sure, we did that. And now I'm going to try and finish this, but it mightn't be on the video. But anyway, y dashed of 3 I have to go really, really, really fast here. So I'm putting in x equal to 3 into this. So this is minus 36 over 2 is minus 18. 3 minus 1 is 2 squared is 4. Now this is 3 minus 5. That's the square bracket of a negative. That's 0. Or a was... Okay, probably ran out of time by now, but anyway. Or a was, where am I? 36 divided by 2 is 18. By 3 squared is 9, plus ma, which is minus 30 times 3. And this should give me 0. Minus 18 by 4, plus 18 by 9, minus 90. Yes. So hopefully that all fit in the video. Verify. So the slope is 0 at 3. And that shows that the maximum deflection is at 3.